You know, we have this habit of talking about the cloud like it's like some sort of magic trick.
Right, like it's just this weightless thing.
Exactly. Like every time you ask an AI a question or, stream a video or save a photo, the data just sort of weightlessly materializes out of thin air.
Yeah, but the reality is incredibly heady.
It is. The cloud isn't a cloud at all. I mean, it is millions of incredibly hot, incredibly loud metal server racks sitting in these warehouse-sized buildings across the globe.
Just sucking up unbelievable amounts of electricity.
And fresh water, too, just to keep functioning. So, welcome to today's deep dive.
Glad to be here for this one.
Because today, we are looking at a move that sounds like, well, pure science fiction, but it is actually happening right above our heads right now.
The massive February 2026 acquisition.
Yes, the acquisition of the artificial intelligence company xAI by the aerospace giant SpaceX.
It's just wild to even say out loud.
It really is. And for you listening, our resident learner, we are looking at this through the lens of a phenomenal, highly detailed Spanish language source called De las Estrellas a la Inteligencia.
Or From Stars to Intelligence.
Right. And our mission today is to cut through the sci-fi hype and figure out exactly why this merger happened, what it means for the future of AI, and ultimately, whether putting AI in space is a stroke of absolute genius or a complete logistical nightmare.
Which is the trillion-dollar question here.
Literally, okay, let's unpack this because we need to start with the sheer scale of this deal, which is staggering.
Oh, absolutely.
When the rumors first started circulating earlier this year, people were throwing around numbers like a $58 billion buyout.
Which is already huge.
Right. But looking at the verified reality, it is so much bigger. xAI is valued at around $250 billion, and SpaceX
Sitting at an estimated valuation of $1 trillion.
$1 trillion. Put them together under one roof, and you're looking at a combined entity worth $1.25 trillion.
Yeah, it forces a complete recalibration of how we view corporate power. I mean, we really cannot view this merely as one tech company absorbing a smaller tech company just to get their software.
Right, it's bigger than that.
Much bigger. This is a historic convergence of AI and critical infrastructure. It is the merging of the most advanced digital brains we have with the physical hardware that literally connects the entire globe.
Not just buying the code, but buying the entire delivery system.
Exactly.
And that brings us to the core mystery here. Like, we understand the valuation is massive, but why put AI in space at all?
It seems counterintuitive.
Right, because building warehouses on the ground is something we already know how to do.
Yeah.
So to understand this cosmic ambition, we really have to look at the earthly crisis driving it, which is energy.
Yeah, the energy problem it's severe.
Modern generative AI is devouring power at a frankly terrifying rate.
Terrifying is the exact right word.
Yeah.
Because by 2030, terrestrial AI data centers are projected to consume tens of gigawatts of power.
Wow, tens of gigawatts.
And for context, tens of gigawatts is not just like a rounding error on a utility bill. That is the energy consumption equivalent of entire mid-sized nations.
Which is just unsustainable.
Completely. Our traditional power grids were built to handle, the morning surge of toasters and office buildings turning on. They were not built for millions of interconnected GPUs constantly crunching the entire sum of human knowledge.
So we are hitting a hard physical limit down here.
We are.
We literally cannot generate and distribute enough electricity to these terrestrial data centers without either risking total grid collapse or just completely obliterating our global climate goals.
Which leads us directly to the orbital solution.
Right.
The idea is to move these data centers into low Earth orbit, specifically into sun-synchronous orbits.
Okay, bring that down for us.
So if you place a satellite in a sun-synchronous path, it essentially rides the Terminator line. That's the border between day and night on Earth.
Okay.
So by riding that line, the satellite would be exposed to sunlight continuously, like 24/7.
Which elegantly solves the energy generation side of the equation.
Exactly. You aren't burning fossil fuels to power your massive AI models. You are drinking solar energy straight from the source without any atmospheric interference or nighttime downtime.
You completely bypass the terrestrial power grid.
Yep. And what's fascinating here is that concepts of scalable orbital computing are actually backed by highly credible academic evidence.
Wait, really? It's not just corporate hype?
Not at all. Research from Google Research, the journal Nature Electronics, and even Penn Engineering have all actively validated the physics and the viability of moving computational infrastructure into orbit.
Okay, here's where it gets really interesting because the best way to visualize this shift is to look at your own house.
Oh, I like this analogy.
Yeah, imagine you have a high-end, ridiculously powerful gaming PC. It's got the best graphics cards, the fastest processors, but every time you turn it on, it generates so much heat, your bedroom basically turns into a sauna.
Right.
And it draws so much power, it keeps blowing the main circuit breaker for your whole house.
Yeah, so you literally cannot run it inside anymore.
Exactly. Your solution, you move the whole setup outside, plug it directly into a massive solar panel, and just let the winter air cool it down.
Except in this scenario, outside is low Earth orbit.
Right. And the solar panel is a multi-billion-dollar satellite constellation.
It makes perfect sense when you frame it like that. You are outsourcing the environmental burden. You take the immense heat and the catastrophic power draw out of our fragile earthly ecosystem entirely.
And place it where energy is abundant and space is infinite.
Exactly.
So the theory makes a lot of sense. But transitioning from the why to the what is this $1.25 trillion mega corporation actually planning to build?
Well, the roadmap breaks down into two distinct phases.
Okay.
You've got the short-term goals, roughly between 2026 and 2028, and then a massive long-term vision for 2030 and beyond.
Let's start with the immediate reality. The short-term goal is integrating xAI's models, specifically the Grok AI, directly into the existing Starlink network.
Right, to optimize it in real time. Starlink is already an expansive network of thousands of satellites providing global broadband.
Yeah.
By injecting an intelligence like Grok directly into that system, you transition the network from a static delivery mechanism into an autonomous thinking organism.
Wow. So it's actively managing itself.
Yes. The AI can instantly calculate the most efficient routing for data packets across thousands of moving orbital nodes. It anticipates network congestion and dynamically reallocates bandwidth before a user down on Earth ever experiences a drop in speed.
So it's performing autonomous satellite maintenance on the fly.
Exactly. And beyond just network health, it unlocks true edge computing from space.
Okay. What does that mean in practice?
Well, normally if a satellite gets data, it has to beam it down to a terrestrial server farm, wait for it to be processed, and then the answer gets beamed back up and then down to the user.
Which takes time.
Right, it creates latency. But with edge computing, the satellite itself does the analysis right there in orbit. It just beams the final answer straight down.
So the reduction in latency is monumental.
It really is. Like if a sensor in the Amazon rainforest detects an anomaly or an agricultural drone in a remote field needs rapid terrain analysis, saving those milliseconds of transmission time transforms what the technology can actually do in the physical world.
The real-world applications of that are phenomenal. Like, we're talking about beaming incredibly low-latency AI tutors into remote communities in Colombia.
Yes.
Places where laying traditional fiber optic cable across mountains and jungles is geographically and economically impossible.
Or even consider SpaceX's own operation.
Oh, true.
Imagine Grok analyzing complex telemetry data from a massive Starship rocket mid-flight. It could instantly calculate fluid dynamics and trajectory adjustments without waiting for ground control in Texas to run the numbers.
So you're bringing the computational brain as close to the physical problem as possible, regardless of where that problem is on the planet.
Or above it.
Yeah.
But that localized optimization is just the foundation.
Right, the short-term stuff.
Yeah. The long-term vision, looking past 2030, scales this up to a constellation of up to 1 million networked satellites.
1 million.
1 million.
Yeah.
Creating a grid with massive, unprecedented computational capacity. And the stated driving force behind this architecture is specifically to support future human missions to the Moon and Mars.
Wait, so is the short-term goal basically just putting a really smart brain inside our space Wi-Fi, while the long-term goal is building a planetary supercomputer?
In essence, yes.
That is wild.
Well, a planetary supercomputer is not just a luxury for a Mars colony. It's actually a fundamental survival requirement.
Because of the distance.
Exactly. The speed of light is a hard universal speed limit. Earth and Mars are vastly far apart, meaning a radio transmission can take up to 20 minutes to travel just one way.
Right.
You cannot have a Mars colony relying on an AI data center physically located in California to manage its life support systems or analyze sudden geological data.
Because a 40-minute round-trip lag would be deadly?
It would be. They need their own massive, independent computational infrastructure waiting for them in orbit.
And while that infrastructure is being built and tested around Earth, It democratizes knowledge in a profound way down here for us.
Absolutely. It provides high-speed, top-tier AI access to anywhere on the globe.
Mhm.
A cargo ship in the middle of the Pacific Ocean or a research tent in Antarctica would have the exact same computational power at their fingertips as an office in Silicon Valley.
And requiring no local physical infrastructure other than a receiver dish.
Exactly.
I mean, it paints this glowing, almost utopian picture, a web of intelligence surrounding the Earth, solving our energy constraints, and beaming education to every corner of the globe.
It does sound great.
It does. But I think it is time we pivot to the cold, hard reality of physics here.
Yes.
Because space is not a friendly, welcoming environment. It is violent, chaotic, and it is terrible for delicate electronics.
It is arguably the most hostile operating environment we know of, which is exactly why the scientific community is pushing back so loudly on the feasibility of this massive scale-up.
So let's dig into those technical hurdles, starting with radiation.
Okay.
Down here on Earth, our thick atmosphere and magnetic field do an excellent job of shielding our computers from cosmic rays and solar flares.
We take it for granted.
We really do.
Wow.
But up in orbit, you lose that protective blanket. A single high-energy cosmic particle striking a computer chip can cause what's called a bit flip.
Right. Changing a 1 to a 0.
Exactly. And if that bit flip happens in an autonomous navigation system, you suddenly have a satellite careening off course.
And to survive that environment, these orbital servers require incredibly dense, heavy physical shielding.
Which is heavy to launch.
Very heavy. Or they have to be built using specialized radiation-hardened chips.
Right. Rad-hard architecture.
Yeah. And rad-hard architecture is historically much more expensive to produce. Plus, it runs hotter and is inherently less powerful than the cutting-edge standard processors we use in terrestrial data centers.
So you are already compromising on raw computational output just to survive the environment.
Exactly.
And that brings us to the cooling paradox.
This is a big one.
Yeah. Earlier, we used the gaming PC analogy, talking about putting the hardware outside in the winter air to keep it from melting down. Space is freezing, obviously, but a vacuum has no air and no water.
Which creates a massive thermal bottleneck.
Right. Down here, data centers use huge HVAC systems and liquid cooling loops, relying on conduction and convection, basically using air or fluid to carry the heat away from the processors.
But up there, in a vacuum, you lose all of that. You are stuck with pure thermal radiation as your only cooling mechanism.
You just have to radiate the heat away as infrared light.
Yeah. And the thermodynamic reality is that radiation cooling in space is actually significantly less efficient than a standard terrestrial liquid cooling system.
Keeping an array of massive AI servers from melting their own circuitry requires enormous, highly complex radiator panels. And that adds incredible weight and volume to every single satellite.
Which directly impacts the economics of launching them.
Exactly. And speaking of the hardware, these satellites don't last forever. The physical degradation from thermal cycling, going from extreme heat to extreme cold, plus micrometeoroids, means hardware in orbit only has a functional lifespan of about 5 to 6 years.
Right, before the satellite's orbit decays and it burns up in the atmosphere.
So if the master plan is a constellation of 1 million satellites, you are talking about replacing hundreds of thousands of nodes every single year.
Which instantly brings up the nightmare scenario for anyone working in aerospace.
Kessler syndrome.
Kessler syndrome. It is the theoretical tipping point where the density of objects in low Earth orbit becomes so high that a single collision generates a cloud of high-speed shrapnel.
Like in the movies.
Yeah, exactly. That debris, traveling at 17,000 miles per hour, shreds through other satellites, creating even more debris, and it triggers an uncontrollable, catastrophic cascade.
It could literally lock humanity out of space for generations, making orbital launches totally impossible.
Right. And launching and constantly refreshing 1 million heavy server satellites exponentially increases the statistical probability of that cascade happening.
There is also a major distinction the scientific consensus draws regarding the type of computing that actually makes sense in orbit, right?
Yes. They caution that while an orbital setup is fantastic for inference, it is a terrible environment for AI training.
Okay, that is a crucial distinction. Break that down for us.
So inference is when you ask an already trained AI model a question and it gives you an answer. That requires relatively low computational overhead.
Okay.
But training a massive new AI model from scratch, that requires networking thousands of GPUs together and moving petabytes of data back and forth constantly.
It's super data heavy.
Incredibly. Accomplishing those massive AI training workloads across thousands of moving satellites that are trying to communicate via lasers is just incredibly inefficient.
So it makes far more logistical sense to keep the heavy lifting of training down on Earth, where hardwired fiber optics can handle the throughput.
Exactly. The orbital brain is highly effective at thinking on its feet and applying knowledge, but the intensive, deep studying still needs to happen in terrestrial server farms.
Which forces me to push back on the entire sustainability narrative driving this merger.
Go for it.
Because the initial hook was that we are saving the Earth's power grid. But if we have to replace these floating servers every 5 to 6 years, and we have to launch them on massive rockets, aren't we just trading terrestrial grid emissions for astronomical amounts of rocket exhaust in a massive cloud of space junk?
It's a fair point.
Like, how is that actually a greener solution for the planet?
Well, if we connect this to the bigger picture, your skepticism hits on the exact environmental accounting problem scientists are actively debating right now. Yes, once a satellite achieves orbit, its daily operations run on clean, continuous solar energy. But achieving orbit carries a massive carbon and resource footprint.
Right, rockets burn fuel.
A lot of it.
Yeah.
Even utilizing SpaceX's reusable Starship architecture, which drastically drives down the cost and emissions per individual launch. The sheer unprecedented volume of launches required to maintain a million-node constellation is staggering.
So you have to rigorously weigh the theoretical green energy of operating in a vacuum against the very real environmental, economic, and atmospheric costs of a never-ending rocket launch cadence. We are saving gigawatts on the ground, but we are burning thousands of tons of propellant in the upper atmosphere to do it.
And we're relying entirely on a single corporate entity to manage that unprecedented launch cadence safely.
Right, without triggering an orbital debris crisis that ruins space for everyone else.
It is an immense concentration of responsibility and risk.
Well, we've covered an incredible amount of ground in orbit today.
We really have.
We've explored the audacious $1.25 trillion reality of SpaceX absorbing xAI. We've looked at the desperate, energy-driven need to move AI infrastructure into sun-synchronous orbits to harvest that continuous solar power.
Yep.
And we've faced the brutal constraints of orbital physics,
Fine.
the constant bombardment of cosmic radiation, the paradox of trying to cool massive servers in a vacuum without air or water, and that relentless, potentially atmosphere-damaging need to replace decaying hardware.
It represents a profound, paradigm-altering shift in computing architecture. We are basically watching the transition from a purely terrestrial model to a deeply integrated, multi-layered orbital model.
So what does this all mean for you, listening right now?
The ultimate takeaway.
Yeah. The ultimate takeaway is that the internet and the artificial intelligence systems you rely on for work, navigation, and creativity are actively decoupling from earthly infrastructure.
It's a huge shift.
The days of relying entirely on a physical fiber optic cable buried under your street or a server farm down the highway, those days are ending.
And this orbital shift promises unprecedented, high-speed, intelligent access for every human being on the globe, completely independent of local geography.
But it also means immense, almost incalculable infrastructural power is being consolidated away from public utilities and into the hands of one single corporate entity.
And this raises an important question, one that serves as a final critical hurdle in the analysis: the issue of data control and national sovereignty.
Oh, right.
For the entirety of human history, critical infrastructure has been strictly tied to geography. A data center physically located in Germany is subject to German laws.
Makes sense.
A server farm in Japan rigorously follows Japanese privacy regulations and data protection standards.
Because it sits on their sovereign soil, their government has jurisdiction over how that data is handled.
But this new infrastructure doesn't sit on sovereign soil.
Yes.
It flies over every border on Earth at 17,000 miles per hour.
Which leaves us with a final, slightly unsettling thought for you to mull over today as you look up at the night sky. We started by revealing that the cloud is not actually a cloud, but heavy metal boxes sitting in warehouses governed by local laws. Well, those boxes are finally leaving the ground.
They're heading up.
But if the ultimate repository of human knowledge, all of our sensitive global data, and the world's most powerful artificial intelligence are physically floating in the vacuum of space far above any country's borders or jurisdictions.
It's a big question.
Exactly. Whose laws exactly do those orbital brains follow?
We are entering a completely unprecedented frontier of international law, governance, and human connectivity.
Thank you for diving into the stars with us today. Keep looking up and keep questioning what exactly is looking back down at you.